In this video, we are going to talk about numerical integration. We'll explain what that is in a minute, and we're going to also talk a little bit about how we can do calculus and the techniques of integration in some real-world settings when we don't necessarily have functions to describe our rate of change. So first, let's talk about what numerical integration is. Numerical integration is what we do when all else fails. So far we have been learning techniques of integration, things like partial fractions, trigonometric substitutions, integration by parts, and so on. And some of those techniques were pretty difficult to get all the way through a particular problem. And it gets worse than that because there are plenty of functions for which we just don't have good methods of integrating. And yet, it's very often the case that we need that antiderivative, or maybe not the actual antiderivative as a function, but maybe we need a definite integral that pertains to that antiderivative. That is, we'd want to use the fundamental theorem of calculus to use an application of an integral, such as finding area or finding a total of something. So, the thing that we're going to talk about with numerical integration is we always have the option of going back to square one and doing some type of Riemann sum. And that's what we're going to do here. For us, we're going to use Excel, and I'll also show you a little clip, if you're using a function, in Mathematica for ways to do numerical integration. So the other thing that we're going to do is take a look at an example, like the one that's up on the screen right now, of times in your life where you may want to use the idea of an integral. You have a rate of change, and you want to use that rate of change to get information related to area or a sum. Remember, where integrals are just sums, to give us a total change to something. So here's the first example that we're going to work through. We've got a car driving through a subdivision, and a ball bounces across the road. And the ball is about 200 feet in front of the car. Now, if you see a ball, as I hope you learned in driver's ed, that rolls across the street, you really ought to slam on your brakes, not because of the ball, but because of the fact that there's a child probably running after it that may not look in the street for a car, and you definitely don't want to hit that child. So we're going to assume that inside this car there's a passenger, very worried, needs a distraction, and starts to notice, takes a look at the time, and takes a look at the speedometer. So here we have different units of time, and the passenger of the car is looking at the clock about every half of a second and determining the speed of the car in feet per second. And so we have this chart of how fast the car was going. Initially, the car was going 60 feet per second, and then naturally the car begins to slow down until eventually, 4 seconds later, the car has come to a stop. So what we have is a rate. We have the way in which the number of feet the car is traveling at a given time is changing. The units that we have here are feet per second. And what we're interested in, ultimately, is the question of how far has the car traveled. Now, distance is rate times time. And we don't know. The car's speed is changing constantly. All we have is this observable information. We have no function giving us the precise speed of the car at time t. We just have these little snippets of observation that we can use. So the very first thing we'd like to do is draw a graph of the car's speed as a function of time. Now we could do that. We could just get out some graph paper and plot it. Let me show you how to do something like this in Excel and give you some helpful tips for cool tools we can use in Excel. So let's open it up, and let's try to copy down the information from the problem into Excel. So in this first column, I am going to type the amount of time that's gone by. 0 seconds, half a second, 1 second. I could keep entering, it's not very hard, but Excel is really good at patterns. So what I can do is highlight these cells and say, Excel, for that pattern, just keep it going for a while. And drag it down, and Excel catches on to that pattern and fills it in with what it thinks I mean. So that's kind of nice. The next column, I'm not so lucky. There isn't a pattern, that's part of our conundrum. So I'll just go down the line and enter what it is we have on the sheet. Finally, I'm going to stop. So I've taken this table from the worksheet and I've entered it into Excel, make Excel larger, Now, I can tell Excel to graph that for me. So let's go to Insert, and let's click on Recommended Charts. Now, one of the charts we might like is this one right here that sort of shows time across the x-axis, and it shows our speed going up. It's got these little rectangles inserted for us, but I kind of like it to be dots with some lines connecting, so we have some idea of what was going on in between. So here's another one that they've recommended for us. Let's go with this one. Insert that chart and bring it up here. Now, if I were doing this for somebody other than myself, I'd probably come up here and I would create a title for this chart, because charts should always be descriptive. I would say something speed over time along those lines, and leave it that way. So here's our graph of our speed as a function of time. Let's return to the worksheet. That was part 1. Part 2 says, approximately how many feet did the car travel in the first second after braking? Well, we don't know exactly, but we can get a good idea. We could take this first second and say we have a little bit of snippet of information. Right away we were going 60 feet per second. We immediately braked and slowed down. And then at about half a second we were going 57 feet per second. And at 1 unit of time we were traveling 54 feet per second. One thing we could do is use that formula, distance is rate times time, and take this rate, 60 feet per second, and assume we were traveling that 60 feet per second for the entire second, and say, we went 60 feet. Well, that's an estimate. It's an overestimate, because we know that we started going slower for some of that time. We weren't traveling at 60 the whole time. Conversely, we were traveling 54 feet per second or faster the entire time. We could use 54 as a certain amount of an estimate for how far we traveled, and know that the real idea will be somewhere in between. Or we could use all the information that we have, and we could say, let's assume we were traveling 60 feet per second for the first half of a second, and 57 feet per second for the second half, and we could get slightly better estimates in that way. Notice that what we're doing is a Riemann sum. We're taking the unit of time, we're breaking it up into little pieces, and we're using the width of the rectangle in terms of the picture. The width of the rectangle is the unit of time, very small unit of time, and the height of the rectangle is some sort of endpoint of this graph, either the 60 or the 57. And we're coming up with an idea of what this area is. And this area is representing the number of feet we've traveled. Okay. The last question just says, approximately how many feet did the car travel before it could stop? Did you stop in time? Well, let's use as much information as we have, let's use it in Excel, and let's compute over and under estimates, just like we did for the 1 second time span. So let's have our unit of time be this half of a second. So that's using all of our data as much as we can. On the one hand, let's use the left-hand endpoints, which are going to be a speed at which we were traveling that's going to be too fast for the entire interval. And that will give us an overestimate of our distance. And then let's also use an underestimate of our distance. Let's use, graphically, let's use the right-hand endpoint as our height function for each of these to get an underestimate of the distance we've traveled. And we'll know that in the end, the real distance is some sort of compromise. So over here in Excel, let's create a column that has to do with distance traveled. We have rates. We have a rate in this column, and this is time. And in essence, we want to multiply the amount of time at which we traveled by the rate and put that over here. So we're using these little half increments. Let's try to get Excel to match the pattern. What we're doing is we're creating a formula. We want this cell to equal the distance, this first distance over the half second time interval. We want to take a half of a second, which is our distance amount, and multiply it by the rate, which is our time amount, and multiply it by the rate, and we've got 30 feet traveled in that first half of a second. Over here, we want to take the 0.5, which is the amount of time we spent traveling at that speed, multiply it by the rate, and it tells us in the second half a second, we traveled about 28.5 feet, and so on and so forth. What we can do is we can program this formula into Excel and then have Excel try to pattern match so that we don't have to do this clicking back and forth the entire time. So we want this cell to equal, and what we want it to be is always this cell, always the cell A3. If you want to fix a particular component of a cell in Excel, either the column number or the row number, you precede it with a $sign in Excel, and you mean don't change that when you enter it in. So I always want the cell A3. I want both the row, which is 3, and the column, which is A, to always be the same. So I can say let's use the value in column A, row 3. Let's take that and multiply it by, this time we really do want things to change. We want 54, then 48, then 42, then 33 as we drag down. So we want the B part to stay the same, but we want the row to be able to vary. So I'd say $B, always keep the B, but this time, for this particular cell, let's use 4, and you're allowed to change that to adapt your pattern. We multiply it in, we get 27. Now I can click on this cell and just drag it down, and it fills in all the values. You can check some of them to see that they're right, particularly towards here at the end. And you can go over and look at the formula, which it'll put in up here, to double check that it's the right value also. So this is something that's summarizing all these distances. Now, if we want to come up with this over approximation, we want to add up all of these distances over the first half second interval, second half second interval, third half second interval, and so on and so forth, until lastly we're using this height of 6 to travel out here to the 4 to add up this area. So we want to add. Excel can do that too. Excel has a command called sum. So we say equals sum, and we open a parenthesis, and then we select the things we want it to add. We want to start here at 30 and go down till we have a rectangle of height 6. We want to add those things up. And that's going to give us this 165 as an overestimate of the total number of feet we've traveled. If I wanted that underestimate we talked about, I'd start over here on the right, start with the height of 0, use that height of 0 to represent this unit, the height of 6 to represent the height of this rectangle, the height of 12 to represent the height of this rectangle, all the way up until this 57 as the height of this rectangle. So for this cell, I'd want to use the sum from here down to the end. And that would give me this distance of 135. So altogether, we imagine that the car traveled between 135 and 165 feet, somewhere in the middle. We could average them if we wanted to get a better estimate. This cell, let's use it this way, equals this cell plus this cell, and the parentheses, and divide that whole thing by 2. If we average them, 150. We would expect to be a little bit nearer to the mark. So in answer to our question on the sheet, approximately, we feel like the car traveled 150 feet. This is just explaining a little bit of ideology, basically saying that sometimes we need to use numerical integration because we don't have explicit formulas. And the next example I'll let you work through on your own in Excel.